Welcome, sleepy friend, to another quiet evening with the Sleepy Professor. Tonight we're floating on a silver ribbon of moonlight, out across the surface of our great blue planet. We're going to explore something ancient, gentle, and endlessly rhythmic, how the moon, that glowing orb in the night sky, pulls at our oceans and shapes the tides. Whether you're here to learn, to wonder, or to simply drift into sleep, you're in the right place. So fluff your pillow, take a deep breath, and let's begin. What if I told you the earth is breathing, and not just through the rustle of wind in the trees or the whisper of clouds overhead, but through the sea itself? That every few hours, the ocean gently inhales and exhales, rising and falling in a rhythm so old, so precise. It's been moving since long before the first fish wriggled in the shallows. You can't always feel it from the shore, and you might not notice it from a boat, but it's there, steady, vast, and tireless. This isn't poetry or metaphor, it's the tides. And they are the quiet pulse of our living planet. Picture yourself at the edge of a quiet beach, far from crowds and city sounds. The sun has just dipped below the horizon, leaving a silvery twilight brushing the surface of the sea. The air is calm, the sky dimming to deep blue, and the waves are rolling in with a deliberate, almost thoughtful rhythm. They reach up the shore as if curious, pause for a moment, and then slip back, revealing glistening sand and shells like tiny forgotten treasures. You wait, and the same thing happens again. In, pause, out, again and again. There's no urgency, no randomness, just a dependable, hypnotic motion that goes on whether anyone is watching or not. It's easy to stand there and feel as though the entire planet is at peace. But behind this peace is a force of immense scale and elegant complexity. Tides aren't just water moving in and out, they are the visible echo of celestial forces at work. The sea doesn't rise and fall because it feels like it. It does so because something out there, something over 380, 0 kilometers away, is quietly calling it. The ocean hears that call and responds, not with noise, not with speed, but with patience. It listens to the moon. For most of human history, people didn't know what caused the tides. They only knew that they came like clockwork, and that life by the sea had to adapt. In ancient coastal villages, elders watched the shoreline like you might check the time. Fishermen in long-forgotten eras built their days around it, not by understanding gravity or celestial mechanics, but by intuition, by rhythm. They didn't need to know why the water moved. They only needed to know that it would, and it always did. That's the magic of tides. They connect us to something larger, something slow and deliberate and beyond human urgency. In a world that changes fast, where days blur together and time feels like it slips through your fingers, the tide is one thing that refuses to rush. It moves at the pace of the moon. It waits. It returns. No matter what you do, it will be back, pulling the sea in with soft determination, then letting it go again like a deep, endless breath. Even now, as you listen, the tide is turning somewhere. In the darkness, water is surging softly into rocky coves and curling around piers. On another shore entirely, it's pulling away, uncovering seaweed and driftwood, and the damp, salty imprint of what was just underwater moments ago. Somewhere, a child's sandcastle is being gently erased. Somewhere else, a tide pool is being born, brimming with tiny lives that only exist in that in-between world where land meets sea. This is not just nature doing its thing. This is the heartbeat of the ocean, paced by the heavens. The rise and fall you see, or maybe only feel, is shaped by the gravity of the moon, the spin of the earth, and the vastness of space itself. It is ancient. It is global. And yet, somehow, deeply intimate, it touches every coastline, every beach, every harbor and inlet, but it also reaches each of us in quieter ways. Because when you sit beside the ocean and feel the tide creep close and then retreat, it feels personal, like the planet is breathing in time with your own breath. So the next time you stand by the sea and feel the water slowly tugging at your feet, remember, it's not random. You're part of a cycle older than words, deeper than wind, and written into the earth by the moon's gentle pull. The tide has come in again, just as it always has, just as it always will. The moon doesn't shout, it doesn't flash, or roar, or demand attention. It simply rises, slowly, quietly, with that pale silver glow that feels more like memory than light. It's easy to forget it's even there sometimes, hanging above rooftops, drifting through clouds, reflected in puddles and windows and waves. But despite its silence, the moon is constantly reaching out. Not with hands, not with voice, but with gravity. A gentle, invisible invitation extended to every drop of ocean on our planet. And the ocean, vast, deep, and slow to respond, listens. It hears the call and begins to move, pulled not by whim or wind, but by this ancient gravitational whisper that never stops. Gravity is subtle. You don't feel it press against your shoulders or tug at your feet, but it's always there, holding you to the earth, guiding the planets, keeping the stars in place. And the moon, though small compared to the sun, is close, so close that its gravity has a more immediate effect on us, especially on water. Unlike the ground beneath our feet, the oceans are fluid, flexible, and free to respond. So they do. They rise up toward the moon's pull, not in a single crashing wave, but in a slow bulge, a swelling of the sea that follows the moon as it travels across the sky. But this isn't a dramatic lift. It's not a splash or a surge. It's a subtle lifting of the ocean's skin, just a meter or two in most places, though stretched across thousands of kilometers of open sea. Imagine something that enormous, trillions of tons of water, rising almost imperceptibly, obedient to a force that never speaks. The moon doesn't ask. It doesn't command. It simply is. And the oceans, as if enchanted, rise to meet it. As the Earth spins on its axis, different parts of the planet move through this bulge of water. When a coastline moves into the bulge, the tide comes in. When it moves out, the tide goes out. This is the basic rhythm we see every day, high tide and low tide, over and over again. But it's not just about one bulge. Something more elegant is happening. While one side of the Earth faces the moon and experiences this gravitational pull directly, the other side, the one facing away from the moon, experiences something equally strange. You might expect only one high tide, right? The ocean being pulled toward the moon should lift the water closest to it. But then, why are there two high tides each day in most places? Why does the ocean swell on the opposite side of the Earth as well, where the moon's pull should be weakest? The answer lies in the delicate balance of forces, and in the fact that gravity doesn't pull everything equally. It's here that things get wonderfully, quietly strange. While the moon pulls on the side of Earth facing it, it also pulls on the Earth itself, on the rocks and soil, and solid ground beneath your feet. It pulls the entire planet toward it, ever so slightly. But the ocean on the far side, the side facing away, isn't pulled quite as strongly. That water lags behind a little, not out of laziness, but because it feels less of the moon's pull. So while the Earth shifts forward under the moon's gravity, the water on the far side is briefly left behind, forming a second bulge. It's not being pulled outward, but it appears to swell away from Earth's surface because everything else, Earth and the near-side ocean, is moving more eagerly toward the moon. The result is a kind of stretching. The oceans are drawn out into an elongated shape, like a slightly squished sphere, two bulges, one facing the moon and one on the opposite side. As Earth rotates through these bulges, any given spot on the surface will experience two high tides and two low tides each day. A quiet, seamless pattern, unfolding every 24 hours and 50 minutes. A time marked not by clocks, but by the moon's position in the sky. This is what makes the moon's pull so fascinating. It's not just about the strength of its gravity, but the unevenness of it, the differential force. That small difference in gravitational pull across the surface of our spinning planet is what creates this elegant ballet of water. It's a slow-motion waltz between the moon and the sea, with the Earth twirling in the middle, always spinning, always moving through tides that never quite stop to rest. And it's all so subtle, so consistent, so easy to miss if you're not paying attention. But once you know it's happening, once you understand that the moon is always out there, pulling, coaxing, guiding, every rising wave, every receding shoreline feels different. It feels like part of something enormous and ancient, something still playing out above your head while you sleep. while you dream, while you simply breathe. The moon is calling, and the ocean, faithful as ever, answers, twice a day, every day, with a slow, quiet movement that never grows tired. It seems simple at first. The moon pulls on the ocean, and the water rises, a straightforward cause and effect. You might imagine one great bulge of water following the moon as it moves overhead, like a loyal companion trailing behind in the sky. But the ocean doesn't behave quite so neatly. It doesn't rise in just one place. Instead, something more curious happens, something that makes gravity feel less like a law and more like a quiet trickster, revealing a deeper layer of the universe only when we look closely enough. Because as strange as it sounds, the moon causes not one, but two high tides at the same time, one on the side of Earth facing the moon, and another on the exact opposite side. And understanding why is like peeling back a curtain on one of nature's most elegant illusions. Start with the side of Earth that faces the moon. The explanation here is easy to follow. The moon's gravity pulls on the ocean more strongly than it does on the rest of the planet's body, so the water on that near side stretches out toward the moon. It's the gravitational equivalent of a subtle lean. Not a wave crashing forward, not a flood or a surge, just a slow, vast movement of water rising upward in response to the moon's silent call. That's the first high tide, and it's exactly what you'd expect if gravity were the only part of the story. But now consider the opposite side of the Earth, the one facing away from the moon. You would think that if gravity causes a bulge on the near side, the far side would sag, or flatten, or at least not rise. After all, the moon is farther away from that part of the ocean, and yet, the water on this far side lifts too, forming a second bulge, almost a mirror image of the first. At first glance, it seems impossible. How can the moon be pulling water in two directions at once? How can it stretch the ocean on both the near and far side of the Earth? It sounds like a paradox. But the answer lies not in how gravity pulls, but in how it pulls differently depending on where you are. Gravity isn't a single blanket force that acts equally across all distances. It weakens with space. The moon pulls most strongly on the side of the Earth closest to it, slightly less strongly on the center of the planet, and even less on the far side. And this uneven pulling, this difference in gravitational strength across a single object, is what we call a tidal force. It's not the strength of the moon's pull that matters, it's the variation in that strength across the Earth's surface that creates the tidal bulges. So what's really happening? The moon pulls the ocean toward it on the near side, yes, but it also pulls the solid Earth itself, dragging the rocky center of our planet ever so slightly toward it. And because the water on the far side isn't pulled quite as strongly as the Earth's center, it's effectively left behind. Not pulled outward, exactly, but less pulled inward. And in that difference, a second bulge appears. The Earth is moving slightly more than the water, and the ocean on the far side seems to rise in response, not from a direct pull, but from a gentle lag. It's a bit like spinning in a circle while holding a bowl of soup. The liquid sloshes outward on both sides, not because you're pulling it in both directions, but because different parts of the soup respond differently to the movement. One part surges ahead, another lags behind, and the result is a shape that's no longer round but stretched. The Earth behaves similarly, with the oceans reacting not just to gravity, but to differences in gravity across the planet's surface. These two bulges, one toward the moon, one away, rotate with the Earth. And because our planet spins beneath them, any given point on Earth moves in and out of both bulges over the course of a day. That's why we experience two high tides and two low tides in roughly 24 hours and 50 minutes. The ocean isn't just following the moon's path. It's shaped by an invisible tug-of-war between motion, mass, and gravity. The rhythm isn't fixed by human clocks, but by the moon's pace as it orbits the Earth and the Earth's own rotation beneath this watery distortion. There's a poetic tension in this pattern. Water is being pulled and stretched, not just toward the sky, but across the skin of the world. Every coastline is part of this stretch. Every bay and harbor lifts and lowers with it, and even though the change might be only a meter or two in height, it represents the movement of incomprehensible volumes of water. Entire seas tilting slightly, leaning toward and away from the moon in a kind of cosmic sway. This is why the tides are more than just sloshing water. They are the result of Earth's shape, its motion, its oceanic flexibility, and the moon's persistent, uneven gravitational whisper. They're born from balance, between the moon's pull and Earth's spin, between motion and mass, between the forces that draw us in and the forces that let us go. So the next time you watch the tide roll in, know that it's not just the sea being pulled toward the moon, it's the entire planet responding in different ways, and the ocean quietly revealing the difference. One tide, created by gravity's embrace, the other, by gravity's absence. Together, they are not opposites, but partners in a dance that has been turning for billions of years, stretching the sea and spinning the earth beneath it, again and again. As powerful as the moon's pull on the oceans may be, it's not the only player in this elegant ballet of water and gravity. High above, shining far more brightly but much farther away, is another force, one we often associate with warmth, with daylight, with the rhythm of our days, the sun. It's easy to forget that the sun, too, has gravity. It's so enormous, about 27 million times more massive than the moon, that it holds the entire solar system in orbit. And though it sits nearly 400 times farther from Earth than the moon does, its gravitational influence still reaches us, including the oceans. What's fascinating is how the sun's pull, though weaker on tides than the moon's, works in harmony or in opposition, shaping the tide's behavior in subtle but powerful ways. The result is a tidal pattern that breathes with both the moon's quiet insistence and the sun's overwhelming presence. Together, they create crescendos and calms in the ocean's rhythm, rising and falling not just with the moon, but with the changing geometry of space. Imagine, for a moment, the Earth caught between the moon and the sun. This happens during two familiar times: the full moon, when the moon is directly opposite the sun in our sky, and the new moon, when the moon sits between us and the sun, hidden in daylight's glow. During both of these alignments, the gravitational forces of the moon and the sun are pulling along the same line. Their forces combine. They don't cancel each other out, but reinforce one another. The moon's tug and the sun's tug are working together, and the result is a stronger, more exaggerated tidal response. Higher high tides, lower low tides, a deeper breath from the ocean. These are known as spring tides, not named for the season, but from the older meaning of spring, as in to leap or surge. And the ocean, in these moments, does just that. It surges. The difference between high and low becomes more dramatic. Shorelines stretch further, mudflats widen, and harbors feel the pull of the sky more intensely than usual. 2 weeks later, the alignment shifts. The moon moves to the first or third quarter phase, forming a right angle with the Earth and the sun. The sun pulls in one direction, the moon in another. Now, instead of working together, they are partially opposing each other. Their gravitational effects don't cancel entirely, but they interfere. The moon still pulls at the ocean, and so does the sun, but they're each tugging at different angles, causing a kind of gravitational compromise. The result is a gentler tide. High tides are not as high. Low tides are not as low. The overall range is narrower, more subdued. These are called neap tides, a word that means scarce or lacking, and that's exactly what they are. A calm moment in the ocean's rhythm, a sigh rather than a gasp. This waxing and waning of tidal intensity, repeating every 2 weeks, is part of a larger pattern governed by the moon's orbit and its changing position relative to the sun. The tides don't just rise and fall each day, they swell and relax across the month, guided by the shape of the moon in our sky. That familiar sequence of crescent, quarter, gibbous, full, and back again isn't just a visual change. It's a gravitational metronome, a signal of what the oceans are about to do. And the Earth listens. So do the animals. And so, whether we realize it or not, do we? There's a kind of music in this, a pattern of harmony and dissonance, of swelling tides and softened ones. When the moon and sun are aligned, their combined gravity conducts a high, sweeping note across the ocean's surface. When they pull at odds, the tone drops, quieter, gentler. The ocean doesn't simply respond to one force, it responds to two. And like any good duet, their relationship is not always in agreement. Sometimes they sing in unison, sometimes in counterpoint. But the tide always follows, pulled between them. And there's something else. Because the moon's orbit isn't a perfect circle, it's slightly elliptical. Its distance from Earth changes over time. When the moon is closest to us, a point called perigee, its pull is even stronger. If this close approach happens to align with a spring tide, when the sun and moon are already pulling together, the result is a particularly strong tide, sometimes called a perigean spring tide, or more playfully, a king tide. These are the moments when the ocean stretches its limits, when coastal streets flood more easily, and the line between land and sea becomes more fluid. They're rare, but regular, predictable, like everything else in the great tidal rhythm. And while these tides can be dramatic, even disruptive, there's also something deeply humbling about watching an invisible alignment in the heavens create a very visible change here on Earth. It's worth remembering that these cycles don't just shape the water, they shape life. In estuaries and tidal flats, the alternating pull of spring and neap tides brings fresh nutrients, oxygen, and opportunity. Some creatures time their migrations, their breeding, even their feeding, to match these gravitational cycles. Fish come closer to shore, crabs emerge from their burrows. Birds that rely on exposed mudflats for feeding must wait until the neap tides roll back and reveal their dinner. The sun and moon are not just moving water, they are stirring the entire coastal web of life. All of this is happening constantly, even now. Somewhere, as you listen, a spring tide is reaching its peak, pressing into a harbor, lifting boats higher than yesterday. Somewhere else, a neap tide is whispering in, quieter, retreating sooner, pausing just a little closer to stillness, and yet it never stops. It only shifts. It flows from strength to softness, from high to low, not because the earth wants it to, but because it must, because it is being played like an instrument by forces beyond its surface. Because the sun and moon are still dancing overhead, and the ocean has always known the steps. It's a beautiful thought, isn't it? That while the moon tugs with quiet focus, and the sun adds its steady power, the earth simply turns beneath it all, moving through this dance with grace. The tides aren't just about gravity, they're about timing, about harmony, about the interplay of forces too vast for us to see, yet intimate enough to touch the shore beside our feet. We may not feel the pull directly, we may not sense the alignment above, but the ocean does. It always has, and it always will. If the moon and the sun are the conductors of the tidal symphony, then Earth is the grand stage upon which this watery performance unfolds. But not all stages are created equal. Some are wide and open, some are narrow and cluttered, and some echo with unexpected resonance. The ocean's response to the moon's pull depends not only on celestial mechanics, but also on the shape of the Earth itself, its coastlines, its ocean basins, its underwater mountains and valleys. These features shape the movement of the tides, guiding and redirecting the ocean's flow like invisible hands, creating a world where the same forces produce very different results, depending on where you stand. In some places, the tides behave just as you'd expect, 2 high tides and 2 low tides, each lunar day, regular and balanced. This is known as a semi-diurnal pattern, and it's common along many coastlines, such as the eastern seaboard of North America. Here, the tidal rhythm follows a steady beat, like a well-practiced melody played twice a day, but in other parts of the world, the rhythm shifts. Some locations experience only 1 high tide and 1 low tide each day. These are called diurnal tides, and they can be found in areas like the Gulf of Mexico, where the unique shape of the sea floor and the surrounding landmass distorts the expected pattern. Then there are places where the tides are mixed, 2 high tides and 2 low tides, but of unequal heights. The ocean here seems undecided, improvising as it goes, as though testing different variations on the same theme. The key to these differences lies in the geography of the ocean basins. Unlike a smooth, round bowl, Earth's oceans are full of irregularities. Underwater mountain ranges, deep trenches, wide plateaus, and narrow channels. All of these features influence how the tidal bulges created by the moon and the sun can move. Picture the tidal wave not as a crashing breaker, but as a slow, massive bulge of water gliding across the surface of the planet. This bulge wants to travel freely around the globe, but it encounters obstacles, continents that block its path, coastlines that reflect and refract its energy, underwater terrain that speeds it up or slows it down. It's like rolling a blanket over a jagged floor. The shape of what lies beneath determines how the blanket moves, where it bunches, where it smooths, and where it cannot reach at all. One of the most dramatic examples of this is the Bay of Fundy, nestled between Nova Scotia and New Brunswick in Canada. This narrow, funnel-shaped bay amplifies the incoming tide in an extraordinary way. As the tidal wave from the Atlantic enters the bay, the narrowing walls and shallow depth force the water higher and higher. Like water being poured into a cone, it rises more quickly as the space narrows. The natural rhythm of the bay happens to match the rhythm of the incoming tide, what scientists call resonance. It's like pushing a swing at just the right moment, again and again. The energy builds, and the result is astonishing. Tides that can rise and fall more than 16 meters, or over 50 feet. Entire harbors disappear and reappear. The ocean pulls back to reveal the muddy seafloor, only to return with roaring momentum hours later. And all of it, every inch of rising water, is driven by the same moon that causes a gentle 1-meter tide somewhere else in the world. In contrast, consider the Mediterranean Sea. Nearly enclosed by land, connected to the vast Atlantic Ocean by the narrow Strait of Gibraltar, the Mediterranean receives very little of the tidal energy that flows across the rest of the planet. The opening is too small, the basin too isolated. Here, the tides barely register. In many places along its coast, the sea appears almost still. Tidal changes are measured in centimeters, and many beachgoers might never notice them at all. It's not that the moon has forgotten the Mediterranean, it's that the sea doesn't have enough room to respond. The geometry of the basin stifles the movement. The music is playing, but the instrument is muted. Elsewhere, the ocean's complexity reveals itself through whirlpools of motion. In open waters, far from shore, there are mysterious points where the tides seem to cancel themselves out. These are called amphidromic points, locations where the tidal rise and fall is practically zero. The water here doesn't move up and down so much as it rotates around a central pivot, spinning slowly in a circular pattern. The tide in these regions is like a slow wheel turning on its axis, with the ocean rotating gently around it. You could float above one of these points and never feel the tide at all, even while distant coasts are rising and falling in rhythm. It's a strange, quiet eye at the center of a watery storm, a reminder that tides are not just back and forth motions, but complex rotations guided by Earth's shape, spin, and structure. And then there's the Coriolis effect, a result of Earth's rotation that causes moving water to veer to the right in the northern hemisphere and to the left in the southern. This subtle deflection influences how tidal waves travel, giving them a spiral motion as they move through the ocean basins. Like water swirled in a bowl, the tides don't just slosh, they spin. They dance around coastlines and islands in vast, slow-moving gyres, shaped by both gravity and the turning of the Earth itself. Even above sea level, geography plays a role in how we perceive the tide. On a gently sloping beach, a change in sea level of 1 meter might uncover hundreds of meters of shoreline, revealing tidal pools, sandbars, and wide flats. On a steep, rocky coast, that same tidal change might barely shift the waterline. The physical shape of the land exaggerates or conceals the tide's effect, changing not the tide itself, but how we experience it. The same celestial forces at work, but a very different story told by the shore. All of this means that the ocean's response to the moon is not uniform. It is diverse, shaped by every ridge and valley, every bend and bay, every contour of the seabed and coastline. The tides are a global phenomenon, but they speak in local dialects. And no matter where you are, whether the tide is thunderous or quiet, predictable or puzzling, it is being shaped by the land beneath and around it. This is why the sea can never truly be tamed or fully predicted by a simple rule, because every shoreline is part of a unique conversation between earth and sky. Some coasts whisper, some shout, and some sing songs so complex they've taken generations to understand. The moon may be the conductor, and the sun its powerful accompanist, but the earth writes its own verses, etched into the rock, hidden in the depths, drawn in the sand by tides that know the tune better than we ever will. If you could listen closely enough, not with your ears, but with something deeper, you might begin to hear it, a rhythm, subtle and steady, pulsing through the world. It's not the ticking of a clock or the beating of a drum, but the ancient cadence of tides. They don't just move water, they move time. Long before humanity invented minutes and hours, before sand flowed through glass or gears turned inside watches, the ocean was already keeping track. The tide was the planet's first clock, marking the passage of time not in numbers but in movement. And for creatures who lived by the shore, animal or human, it became the most reliable pattern in the world. One that still hums beneath the surface of life, whether we notice it or not. In the earliest days of civilization, long before science put names to the moon's pull, people knew the ocean changed in cycles. Fishermen, in ancient Mesopotamia and along the rivers of China, noticed the pattern. Twice a day, the water returned to flood their nets or lifted their boats. Twice a day, it pulled back, revealing mudflats, oyster beds, and hidden channels. These patterns were passed down not as formulas but as traditions, rules of thumb spoken over firelight, etched into the rhythm of daily life. Where modern towns have clocks in towers, ancient harbors had tide markers carved into stone. The sea came in, and it went out, and in that cycle people saw a signal, a guide, a dependable partner that told them when to cast nets, when to launch boats, when to harvest the bounty hidden in the shallows. Even animals learned to read this lunar clock long before we did. Along coastlines across the world, entire species have synced their lives to the tides with astonishing precision. Crabs that emerge only when the water reaches a certain height, clams that open with the flood and shut tight as the water drains away, tiny worms that burrow and wait, counting the hours in their own silent way. These creatures don't use sight or sound to track the tide. They feel it. Somewhere in their biology, a memory is stored, not of specific dates or times, but of rhythm, of movement, of the moon's whisper to the ocean. Some animals take this synchronization to astonishing levels. There are species of fish that wait for a very specific moment during the monthly tidal cycle to come ashore. The grunion, found along the coasts of California and Mexico, time their breeding to the highest of spring tides, those moments when the moon and sun align and the sea stretches just a bit farther than usual. Under the cover of night, and only during certain phases of the moon, they swim up onto sandy beaches and lay their eggs above the usual waterline. Then they vanish back into the sea. 2 weeks later, when the next spring tide arrives and the waves reach that same stretch of sand, the eggs hatch. Tiny fish, born under moonlight, are carried into the water by the returning tide. No one taught them this schedule. They were born into it. Their very survival depends on remembering a calendar written in gravity and salt. And it's not just marine life that takes its cues from the tides. Migratory birds, traveling thousands of kilometers, plan their journeys around tidal events. On the east coast of North America, the red knot, a small but tireless shorebird, times its arrival to coincide with the mass spawning of horseshoe crabs. These ancient creatures crawl ashore during spring tides, laying millions of eggs in the wet sand. The red knots, weary from a journey that spans continents, descend on these beaches just in time to feed. It's a rendezvous orchestrated by the tides, and if either species misses the mark, if the moon's timing is off, or the birds arrive too soon, there are consequences. Energy lost, chicks unfed, a rhythm disrupted. Tides don't just influence when animals move, they shape how they grow, where they live, even how their bodies are built. In the intertidal zone, the area that lies between the high and low tide marks, life must adapt to constant change. Creatures here endure daily floods and droughts, soaking in salt water 1 hour and baking under the sun the next. Barnacles cement themselves to rocks with glue stronger than superglue. Mussels cluster together to trap moisture and survive exposure. Starfish wait for the tide's return to begin their slow-motion hunt. Sea anemones close up tight like clenched fists when the water leaves them, only to bloom open again as it returns. Every species here lives by the same clock, measuring time not in seconds, but in distance. How far did the tide come in? How long has it been gone? These questions matter more than any human hour. And yet, humans too continue to live by this clock, often without realizing it. Coastal communities the world over still plan their days around the tide's rhythm. In parts of the Pacific Islands, fishing trips are scheduled based on lunar phases. In Northern Europe, where tidal flats stretch for miles, people walk across the seabed to reach islands, but only during low tide. Hours later, the same path lies hidden beneath meters of water. Tide tables, printed in newspapers or checked on phones, are not just curiosities, they're essential tools. A harbour master in Scotland needs to know when the next high tide will float a ship out to sea. A surfer in Indonesia waits for the tide to shift before catching the perfect wave. Even beachgoers, seeking the widest stretch of sand, glance at tide charts before packing up a towel. There's a gentle authority to all of this, a sense that something older than cities, older than roads or screens or machines, is still quietly calling the shots. And unlike many forces in life, the tide can be trusted. It doesn't skip a beat. It doesn't arrive late. The moon does its part, the earth responds, and the sea obeys. It's a cycle that can be predicted years, even centuries, in advance. No battery needed, no maintenance required. Just the turning of the earth, the orbit of the moon, and the silent pull of gravity, doing exactly what it has always done. In an age when so much feels rushed and fleeting, the tides offer something rare: certainty, stability, the assurance that some things remain untouched by noise or haste. And for those who pause long enough to feel it, there's a comfort in that, in knowing that while the world above changes in flashes, news, updates, alarms, the world below still moves in waves. Slow, measured, reliable. So next time you notice the ocean rising or stepping back, know that you're witnessing something profound. A measurement not of seconds or schedules, but of connection. The sea answering the moon guiding the earth, and every life caught in between, keeping time in a language written not in numbers, but in tides. We tend to think of the earth as solid, steady, unmoving beneath our feet, a firm foundation, a quiet, constant presence that holds everything else up. Mountains don't sway, sidewalks don't ripple, rock doesn't bend. But what if that wasn't entirely true? What if, beneath all our assumptions, the earth itself was subtly, invisibly moving, responding, ever so slightly, to the same celestial forces that lift and lower the oceans each day? Because the truth is, the solid ground beneath us is not as still as it seems. Just as the moon pulls on the sea, creating bulges of water that move with its orbit, it also pulls on the planet itself, stretching and squeezing the Earth's crust in a phenomenon known as earth tides. They're much smaller, yes, just a few centimeters of motion, but they are real. The ground beneath you is gently rising and falling right now. You just don't feel it. This movement isn't something we notice in daily life. It doesn't tilt buildings or crack sidewalks, but it happens everywhere, all the time, in perfect synchrony with the tides of the sea. When the moon is overhead, or on the opposite side of the Earth, its gravitational pull creates not only a bulge in the ocean, but also a slight stretching of the Earth itself. The land swells upward, imperceptibly, then relaxes again as the moon continues along its orbit. This happens twice a day, every day, like a hidden breath, inhaled by the planet's crust. It's a motion so smooth, so slow, so subtle, that we've lived with it all our lives without even knowing. Scientists can measure it with sensitive instruments, gravimeters, and GPS sensors, capable of detecting changes of just a few millimeters. What they find is extraordinary. Mountains sway, plains lift and sink. Even entire continents experience this rhythmic flexing. The Earth is elastic, like a vast, stiff sponge, always being pulled and released by the Moon's persistent gravity. These movements are called solid Earth tides, and while they don't cause damage, they do remind us of something quietly profound, that nothing on this planet is truly still. Not the oceans, not the air, not even the land. It doesn't stop there. The Moon's pull also affects the way Earth rotates. As the tidal bulges move across the planet, both in water and land, they create friction. The ocean is constantly rubbing against the seafloor and against coastlines. This friction acts like a brake, ever so slightly slowing Earth's rotation over time. Our days are getting longer, by mere fractions of a second, but the change is measurable. Hundreds of millions of years ago, an Earth day might have lasted only 22 hours. Go further back, and the spin was even faster. The Moon, meanwhile, is slowly drifting away, carried outward by the energy transferred from Earth's rotation. Every year, it moves about 3.8 centimeters farther from us. It's not much, barely the width of your fingernail, but over millions of years, it adds up. This gentle exchange of momentum is a kind of cosmic trade. The Earth gives up a bit of its spin, and the Moon moves a little farther away. This process is known as tidal acceleration, and it means that the Earth-Moon relationship is not static. It's dynamic, evolving, shaped by the friction of tides and the stretch of gravity. One day, far in the future, the Earth and Moon will reach a state of tidal locking, where the same side of the Earth will always face the Moon, just as the Moon now always shows us only one face. But for now, we are in a unique moment, one where both celestial bodies are still dancing, still exchanging energy, still influencing each other's pace. It's strange to think that the Moon, distant and silent in the night sky, is not just shaping the oceans, but also slowly altering the length of our days, the rotation of our planet, and even the way continents shift over geologic time. And it all begins with that quiet gravitational pull, so consistent, so patient, that it bends rock and water alike. This influence also reveals itself in more delicate ways. For example, researchers have found that certain volcanic and seismic activities are more likely to occur at specific points in the tidal cycle. When the Earth's crust is stretched by the Moon's pull, it can place just enough additional stress on fault lines or magma chambers to trigger movement. The tides, in this way, act like a hand tapping gently on a pressure point, not causing earthquakes or eruptions directly, but occasionally giving the Earth the final nudge it needs. Even the polar ice sheets aren't immune. In Antarctica and Greenland, as the ocean rises and falls with the tide, it presses on the ice from below and affects the flow of glaciers above. The entire cryosphere, the frozen skin of our planet, responds to this rhythm. It bends and creaks in time with the Moon. And while these changes are subtle from day to day, they leave a mark over time, contributing to sea level shifts and patterns of melting and freezing. All of this paints a picture of a planet that is not fixed, not frozen in place, but incredibly dynamic, soft in places, flexible in others, always responding to the pull of a quiet neighbor overhead. It's easy to think of tides as just a beach phenomenon, something that happens only where water meets land. But the reality is far more encompassing. The entire planet is moving, breathing, reacting. The Earth doesn't just have tides. The Earth is, in some small but profound way, tidal. This thought might change the way you see the ground beneath you. What seems solid is, in fact, bending. What seems constant is being reshaped. And what seems distant, the Moon, shining far away in the sky, is closer than it appears in influence. Every rise of the ocean, every shift in Earth's spin, every subtle lift of the land is a response to its presence. So next time you step outside under the moonlight, remember that the planet beneath your feet is stretching just a little in that very direction. The ground itself is listening, and in its own quiet way, it is answering. There was a time when the Moon hovered much closer to Earth, so close, in fact, that it would have dominated the night sky, filling it with a luminous presence, far larger and brighter than we see today. Imagine looking up and seeing not the gentle disk we know now, but a massive glowing orb, nearly 20 times larger in the sky, casting deep, moving shadows as it pulled on the seas, with an intensity that shaped the very crust of the planet. Back then, Earth rotated faster, spinning through a full day in as little as 5 or 6 hours. The result of this proximity and rapid spin was a world of violent, towering tides, sweeping across young oceans with a force few could imagine. The coastline was not a place of calm waves or gentle tides. It was a chaotic threshold, where entire landscapes could be rearranged with each tidal surge. The Earth, still molten in places, still young and unsteady, was locked in a fiery, watery conversation with its newly formed moon. The moon itself, born from an ancient collision, most likely between Earth and a Mars-sized object called Theia, was forged in violence, a disk of molten debris that eventually coalesced into the companion we now know. In the aftermath of that impact, the gravitational forces between Earth and this fresh moon were staggering. The tides they created were not mere ripples, but colossal pulses of water that sculpted the early continents, redistributed heat, and helped create the complex balance of land and ocean we recognize today. Every single tide was a raw exertion of power, grinding coastlines, carving out basins, and stirring the deep primordial soup in which early life would one day emerge. Over time, though, something changed. It didn't happen quickly. In fact, it's still happening now. With each passing year, the Earth's rotation slows ever so slightly. Not because something is pushing it, but because of friction, specifically the friction between the moving tides and the ocean floor. As tidal bulges are pulled around the spinning Earth, they don't glide effortlessly, they drag. The water sloshes against the land, rubs against itself, and loses a tiny bit of energy to heat. That energy doesn't vanish. It transfers to the moon, nudging it outward in its orbit by a few centimeters each year. It's as if the Earth is handing momentum to the moon, saying, "Here, take this," and the moon accepts it, drifting farther away, inch by inch, year by year. We don't feel this change in our daily lives. You could stand on the same stretch of beach every day for 100 years and never notice the moon getting farther away or the day getting longer. But the evidence is there, etched into stone. Ancient tidal marks preserved in fossilized shorelines and layers of sediment tell the story. In some places, scientists have found geological records showing more than 400 days in a single year, each day shorter than ours now. Over millions of years, those shorter days have slowly stretched, moving toward the 24-hour cycle we experience today, and they will continue to stretch. Hundreds of millions of years from now, if Earth still spins and the moon still circles us, a day might last 25 or even 28 hours. This cosmic exchange, Earth's spin slowing as the moon recedes, is one of the quietest but most powerful transformations in planetary history. It's not loud, it's not sudden, but it's constant and relentless, and it has shaped not just the mechanics of tides, but the evolution of life itself. A slower spin means a more stable rotation. A moon farther away means gentler tides. This shift helped calm the early chaos of Earth's environment, smoothing out the conditions under which life could begin to thrive. Without the moon's stabilizing effect, Earth's axis would wobble more wildly, and the seasons could swing between extremes. The moon is not just our nightlight, it's our planetary anchor. And yet, this stability is not permanent. It is part of a longer arc, a process that continues to unfold. One day, far beyond our lifetimes, far beyond the reach of human civilization, the Earth and Moon will reach a kind of equilibrium, a moment when the Earth's rotation slows enough that it becomes tidally locked to the Moon, just as the Moon is already locked to us. In that distant future, one side of Earth will always face the Moon, and the other side will never see it. The familiar rising and setting of the Moon will stop. Tides, as we know them, will change dramatically or fade altogether, but this will not happen for billions of years. For now, we live in a golden moment, suspended between extremes, when the Moon still circles us and the tides still follow a gentle, predictable rhythm. This era, this exact moment in cosmic history, is special. The moon is just the right distance to shape our tides, but not too close to overwhelm us. The Earth spins fast enough to give us a day we can live by, but slow enough to let the moon do its work. The tides rise and fall with a grace and regularity that's rare in planetary systems. Most moons in our solar system are either too small or too distant to affect their planets much. Some orbit gas giants, lost in the stormy swirl of massive gravitational fields. But our moon, by an extraordinary chance of size and position, has helped Earth become not just a habitable world, but a stable one, a place where the rhythm of life can take root, evolve, and endure. So much of what we take for granted, day and night, the steadiness of the seasons, the gentle rise and fall of the sea, is tied to this ancient relationship, and it is still changing. Right now, as you listen, the moon is slowly moving farther away. The Earth is turning just a little more slowly. The tides continue their patient march across the planet, wearing away stone, delivering nutrients, reshaping coastlines, and writing their presence into the bones of the Earth. The moon is not static. It is a companion in motion, writing history with every orbit, every tug, every subtle change in position. It's easy to forget that we are living through this change, that we are a part of this celestial story, but we are. Every time the tide rolls in and then retreats, we are witnessing the slow passage of time not just on Earth, but between Earth and Moon. It is a dialogue in motion, a relationship that began in fire and is now told in water and gravity. And though we may never see its ending, we are a part of its middle, a brief moment in a long unfolding story. One where the ground we walk on, the sea we listen to, and the moon we gaze at are all quietly reshaping one another, forever. Each time the tide rolls in, lifting boats in their harbors, and sweeping across salt flats and sandy shores, it carries with it something more than just seawater. It carries energy. Vast, silent, relentless energy. Imagine for a moment the weight of all that water, the trillions of tons that move across the surface of the planet every day, pulled by forces you cannot see. Now imagine trying to stop that movement, or redirect it, or catch it, and use it. It sounds impossible, like trying to hold the wind in your hands. But for as long as humans have watched the sea rise and fall, they've wondered the same thing. Could we use this motion, not just to tell time or guide fishing boats, but to generate power, real power, power that lights homes and moves cities? And the answer, remarkably, is yes. Tidal energy is one of the oldest forms of natural power known to humanity. Long before we wired homes for electricity or built wind turbines that spin in mountain passes, people were already finding ways to harness the tides. In ancient coastal communities, particularly in parts of Europe and the Middle East, people built what were known as tidal mills. These weren't high-tech machines or towering dams. They were clever, low stone structures, built into estuaries and inlets, designed to trap water at high tide and then release it at low tide through narrow channels. As the water flowed back out to sea, it turned wooden wheels, which turned grindstones, which turned grain into flour. No wires, no combustion, no engines, just the patient motion of the sea doing its work. These early tidal mills were often built near monasteries or small villages, and many of them remained in use for centuries. A few still stand today, worn smooth by generations of tidal flow, silent reminders that the ocean has been helping us work for a very long time. Fast forward to the present, and the technology has changed, but the principle remains beautifully simple. Use the predictable rise and fall of the tides to move water through turbines, and let those turbines generate electricity. The most well-known example is the tidal barrage. Picture a dam stretching across a narrow coastal estuary. At high tide, seawater flows into a large basin behind the barrage. When the tide begins to fall, the water is held back until the moment is right, then released through turbines that spin and generate power as the water rushes out. It's a little like hydroelectric dams on rivers, but with the ocean instead of fresh water and gravity instead of upstream flow. One of the earliest and most successful of these projects is the Reims Tidal Power Station in Brittany, France. Built in the 1000 960s, it's still operational today and provides electricity for tens of thousands of homes, powered entirely by the slow, rhythmic pull of the moon. But tidal barrages are just one way we've learned to capture the sea's motion. In recent years, engineers have developed underwater turbines, essentially wind turbines placed beneath the surface of the ocean in areas with strong tidal currents. These are called tidal stream generators, and they work by using the movement of water, rather than air, to turn blades and generate power. Because water is around 800 times denser than air, these turbines don't need to move fast to generate significant energy. Even a slow current packs enough punch to keep them turning, hour after hour, twice a day, in tune with the tides. Then there are tidal lagoons, enclosed coastal areas where water is allowed to flow in and out, with the tide through specially designed structures housing turbines. These lagoons can be built to blend with the environment, and because they don't block entire estuaries like barrages do, they offer a more flexible, less disruptive approach to tidal energy. The water flows in with the tide, is captured, then released when the tide retreats, all the while spinning turbines and generating clean, predictable power. And that predictability is key. Unlike wind or solar energy, which depend on weather and daylight, tidal energy follows the moon. It doesn't vary wildly from day to day. It doesn't vanish when clouds roll in or winds fall still. The moon pulls, the tide moves, and the energy comes, always on schedule. We can forecast the tides decades or even centuries in advance. There's something deeply reassuring about that. In a world of uncertainty, where so much of our infrastructure depends on volatile systems, tidal energy offers a kind of quiet reliability. It's the rhythm of the universe made useful. But like all great ideas, tidal energy isn't without its challenges. Building machines that can survive underwater, in a harsh saltwater environment filled with sand, sediment, and marine life, is no small feat. Salt corrodes metal, barnacles cling to every surface. Currents shift, storms roll in. The ocean is not a gentle partner. It demands resilience, creativity, and constant maintenance. And then there's geography. Not every coastline is suitable for tidal energy. You need strong, consistent tides, narrow inlets, or fast-moving currents. Places where the sea already speaks loudly, and where technology can step in without disrupting delicate ecosystems. Environmental concerns are real and important. Tidal barrages, for instance, can change the flow of sediment in estuaries, affect fish migration patterns, and alter salinity levels. The delicate dance of coastal ecosystems depends on the natural ebb and flow of water, and any human-made structure that interferes with that flow must be designed with care and foresight. Engineers and marine biologists work together to monitor these effects, seeking ways to minimize harm while maximizing benefit. The goal is not to conquer the tide, but to cooperate with it, to work with nature rather than against it. And despite the obstacles, the appeal remains strong. There is something undeniably poetic about drawing electricity from the ocean's breath. The idea that every time the tide lifts the sea, it could also be lighting a street lamp, powering a train, or charging a phone. The idea that the moon's ancient pull could hum quietly through our cities, whispering through wires, warming our homes with a power as old as time itself. As technology improves and awareness grows, tidal energy may play a larger role in the world's renewable future, especially for coastal nations where the infrastructure and conditions make it feasible. And perhaps one day, you might live in a place where the lights in your room are powered by the sea just outside your window, where the electricity that toasts your morning bread began as a ripple in the harbor, where the moon, rising silently over the water, is not only shaping the waves, but shaping your life in ways you can see and feel. We often think of energy in terms of motion, flames burning, engines spinning, wires buzzing, but tidal power is different. It is slow, it is quiet. It comes not from combustion or force, but from patience. The tides do not hurry, they do not falter. They arrive, and they retreat, and they do so with the consistency of a breath. To harness that motion is to align ourselves with something much older and wiser than our machines. It is to tap into the rhythm of the planet, the heartbeat of the ocean. the unbroken conversation between Earth and Moon. And in that motion, in that quiet, endless rhythm, we may find not just a source of power, but a reminder of how everything is connected. How what moves out in space moves here on Earth, and how even the gentlest pull, given time, can move mountains of water and light the world. Somewhere right now, under the pale gaze of the moon, the tide is shifting. Water is quietly returning to a stretch of coast it abandoned hours ago, slipping between rocks, soaking seaweed, lifting boats that had rested gently on mudflats just moments before. On another shore, far across the globe, the tide is falling, drawing back like a deep exhale, exposing sandbars, tide pools, and the footprints of crabs and birds that scuttled about while the sea was in. It's happening everywhere, all at once, in an unending cycle that connects every bay, inlet, beach, and harbor across the face of our planet. And though we may not always notice it, this gentle, timeless rhythm is never truly silent. It is the Earth's breath, the ocean's whisper, the moon's enduring touch. To stand at the edge of the sea and watch the tide move is to witness something ancient, something that began long before our first ancestors lit their fires or carved their tools. The moon has been shaping the oceans for over 4 billion years, and in doing so, it has shaped the land, the weather, and life itself. The tides have nourished the coasts, sculpted shorelines, and created the intertidal zones where so many forms of life first found their footing. They have carved estuaries, flooded river mouths, and offered safe passage for migrating fish and shelter for their young. Entire ecosystems rise and fall with the tide, their pulse in sync with the moon's position in the sky. And yet, despite this immense influence, the tide is rarely noticed in the way it deserves to be. It doesn't demand attention. It doesn't arrive with fanfare. It just comes, then goes, and comes again. There's something profoundly humbling about this, that a force so powerful, capable of moving entire oceans, does so with such grace. No violence, no speed, just persistence. The kind of persistence that rewrites coastlines not in days or years, but in epochs. That carves fjords, floods valleys, and creates islands. Not by storm, but by time. The moon's pull doesn't just move water, it moves perception. It slows us down. It invites us to notice, to pay attention to the little things. The way barnacles close just before the tide recedes. The way shorebirds time their feeding with the moment the sand is wettest. The way seaweed waves softly in the current, as though dancing to music we cannot hear. There's something deeply calming in observing this, like being reminded that not everything in life happens quickly, that some of the most meaningful forces work in slow, steady rhythms. That change doesn't always come in flashes. It can arrive quietly and still transform the world. Tides are not just physical events. They are emotional ones. They mark passages in time. The tide you watched as a child, eyes wide as the waves erased your footprints from the shore, is the same tide that will one day wash over a memory. The same tide that returned to greet explorers, to welcome ships home from sea, to cradle the quiet reflections of someone walking alone at sunset. For many people, the tide holds personal meaning, a connection to a place, a moment, a feeling. There is comfort in its predictability, in knowing that, no matter how chaotic the world becomes, the sea will still rise and fall. That even when we feel unmoored, the tide is still tethered to something solid, something ancient, something eternal. And that tether, of course, is the moon, always up there, always watching, always pulling, quietly guiding the oceans without a word. It doesn't need applause or recognition. It doesn't need to be thanked. It simply does what it has always done, keeping time not with minutes or hours but with cycles and phases. Waxing and waning, drawing the seas along in its path like a silent conductor. Without the moon, there would be no tides as we know them, no daily breath of the ocean, no intertidal zones teeming with life, no gentle rise and fall to measure the passing of time. It is easy to take this for granted, to see the moon as just a decoration in the night sky, but it is far more than that. It is the silent partner in our planet's most delicate dance. And that dance includes us. We may not feel the moon's pull the way the ocean does, but it shapes our world in ways both obvious and subtle. It affects the tilt of the Earth, which gives us our seasons. It steadies the spin of the planet, creating a climate in which life can flourish. It creates rhythms in the ocean that nourish and protect, rhythms in nature that we once lived by. And perhaps, deep down, we still do. Maybe there's something in us that remembers. Something in the beat of our hearts, the pace of our breath, the ebb and flow of our own thoughts that echoes the tide. Perhaps we are not separate from this great motion, but part of it, carried along in the same way, shaped by the same forces, drawn by the same unseen pull. And when we pause to feel it, to truly sense the tide, not just as water moving, but as time passing, as gravity reaching through space, as a cosmic thread connecting us to the moon and the sea, we begin to see the world a little differently, more patiently, more reverently. We see the ocean not as a boundary, but as a living clock. We see the moon not as a rock, but as a guide. We see the tide not as background, but as a voice, one that speaks without sound, sings without notes, and never stops moving. So the next time you find yourself at the edge of the ocean, watch carefully. Notice the line where wet sand meets dry. Watch how it changes. Watch how the sea seems to hesitate, just for a moment, before it retreats, or how it creeps forward, inch by inch, swallowing footprints and stones. Listen to the hush as the water returns. Feel the pull in your own breath as the tide begins to rise again. And remember that you're not just witnessing a natural event, you are part of a ritual. One that's been going on since before there were names for stars. One that will continue long after we're gone. The moon pulls, the ocean follows, and the world breathes. Again and again and again.